In this video, I will be explaining you Egoroff's theorem. This theorem is also called as Littlewood's third principle. Okay, so first you can see the statement. First you are going to see the statement. This is the statement. This is the official note that I have. Okay, this is the statement you can see on my note. Okay, the same statement, but for easy understanding I make a note of it. So this is Egoroff's theorem. Let's start with the statement. Here first you are taking a set and the set is having finite measure. That is what in the first line you have. Assume E has a finite measure. E is a set, okay. That set having finite measure. That is how you are assuming, and on this set E, finite measure, set E, you are defining something. That is what this. Let the sequence Fn. You are defining this sequence Fn on this measurable set E, finite measure E. Okay. So this sequence Fn have some of the properties. They are this. Sequence Fn. This is the sequence of this sequence Fn is a measurable function. That is what here you can see. Let sequence Fn be a sequence of measurable functions on E. And this sequence Fn is converges to F. Okay. The sequence Fn, can you see that? Sequence Fn converges to F. And this F is a real valued function. That is what in the next line you can see. And how it is converging? It is converging to F point wise. Okay, if these conditions are there, then for each epsilon greater than, this is what you have to prove. If Fn, sequence Fn have all these properties, then we have to prove this. Okay. Then for each epsilon greater than 0, there is a closed set. There will be a closed set contained in E. If these things are there, then there will be a closed set. That closed set will be inside this finite measure E. Okay, sorry, not finite measure E. That's the blender mistake. This closed set F is contained in the set E having finite measure. Okay, that's better. For which this Fn, the sequence Fn we have, right? This sequence Fn converges to F uniformly on E, and measure of, when you find the measure of E difference F, the value you will get will be less than epsilon. That is what the statement of Egoroff's theorem. I hope you understand. First you are taking a finite measure, a set having finite measure, that is E. On this set E you are defining something, that is on the set E there is a sequence of measurable function, that is Fn, and this Fn converges to F, and that F is a real valued function. It is converging to F point wise on E. Okay. Then these conditions you have to prove here. So here, before proving this Egoroff's theorem, you have to prove a lemma here first. The reason is because here you can see the statement of the lemma that you are going to prove within this theorem. The reason is because, I will tell you. Okay, let's start with the statement of the lemma, and I will tell you when I... Okay. So here, as I told you, before proving this theorem, you have to prove a lemma. Okay. The reason why you are proving this lemma in between this theorem, I will tell you few seconds later. Okay. So here, this is the statement of the lemma. This part, the first part looks similar to our Egoroff's theorem, so that memorizing it is not difficult. Okay, you just memorize it, and in the you no need to memorize the lemma's first part, because this and this are same. Here also you are assuming as you are having a set E and the set having finite measure. On the set E you are having sequence of measurable functions, and this sequence of measurable function converges to small f pointwise on E, and the small f is a real valued function. Then part is different. Okay, here you have to keep in mind the sentences that you have after then. Okay, that is different from this Egoroff statement. So then here eta greater than 0, differentiate it and study so that you don't forget, otherwise you will forget. Then eta greater than 0 and delta greater than 0 is existing. Here epsilon in our Egoroff's theorem, for each epsilon greater than 0, and it will proceed like that. Okay, then eta greater than 0 and delta greater than 0, there is a subset. Here is also a subset existing, that is A. Okay, in our Egoroff's theorem there is F, here is A. Okay, to show the difference, if you use the same set F, if you use the same subset here, then when writing the proof you will confuse about what subset they are talking about. So that is why, to show the difference, here also a subset is existing and you are taking that subset as A, and an index n for which these two conditions you have to prove in this lemma. Okay, I will tell you now the reason why you are proving this lemma in between this Egoroff's theorem is, in the place of, in our Egoroff's theorem you will use this result, that is, in the place of eta in our Egoroff's theorem you will put 1 by n. In the place of delta in our Egoroff's theorem you will put epsilon by 2 power n plus 1. Okay, without proving this lemma you could not apply this delta equal to this value and eta equal to this value in this proof, right? So before you put this, you start proving Egoroff's theorem, you have to prove this lemma. So let's start with the proof of this lemma. The proof of this lemma is not that difficult. First you have to take a measurable set, that is En. En is equal to set of all x belongs to E such that modulus of fk of x minus f of x less than eta. Okay, for all k greater than or equal to n. Okay, here you have nothing to memorize, just you will memorize this statement of this lemma, right? From this statement, when you can write this writing the set, in the place of n just put k and write. Okay, for all k greater than or equal to n, you are taking a measurable set. So from this also, here E1 subset of E2 subset of, when you find E1, that E1 will be the subset of E2 and the E2 will be subset of E3, like that it will goes on like that. And E is equal to, when you find the union of all these E1, E2 etc. up to infinitive, and that resulting value will be our E. That is how you are choosing. Okay, so first you have to consider a set, and then you are saying E1 subset of E2 subset of etc. till infinitive, and then you are saying E is equal to union of all these E1, E2 etc. till infinitive, and then you are taking to this you are taking limit. Okay, not limit, I'm so sorry, you are taking measure on both sides. So when taking measure on both sides, union n equal to 1 to infinitive can be written as limit n tends to infinitive. So limit n tends to infinitive, m of en is equal to m of e. So by the definition of convergence, you can, from this you can write, we have m of en converges to m of e. Okay, in between I think no need to write this. This is just given condition you are writing. Even if you forget to write it, that is not a big problem. Okay, from this you can write, by the definition of convergence, you can write m of en converges to m of e. So by the definition of you are writing the definition. Then by definition of convergence, there exists capital N such that m of e minus m of en less than delta for all n greater than or equal to n. Now in particular, in the place of small n you will put capital N, so that you will get this, and you are taking m common so that you will get this. So now you are putting in the place of en, let en equal to a, so that you will get this. You have proved this condition of the lemma. And then put k equal to n in star star. In the place of k you are putting n, so that you will get this condition. You will be proved this condition also, so that you will get this. So hence the proof. Thus you have proved. I am telling you again, the proof is, according to me, this proof is not proper. Okay. But we have to study it, right? To write it on the examination. Yeah. So next you are going to prove the, you will apply eta equal to 1 by n and delta is equal to epsilon by 2 power n plus 1 to prove our Egoroff's theorem, and I will explain you in another video. Okay.